Right, so unit 6, harmonic motion. So harmonic motion, things that oscillate. There are probably two main setups that you can look for. One of them is pendulums. Right? You guys remember, you guys did a whole lab on pendulums. You guys remember that? Let's say there's some a bob of some mass on a string of some length, where the string itself has negligible mass compared to the bob, right? And say you pull it back to some angle. Now, a lot of times AP specifies they want this to be a small angle, or they might even specify like 15 degrees or less. So maybe I'll jot that down here. Let's say less than or equal to 15 degrees. Because one of those details it comes up. Okay. Then the time period for this to swing back and forth. Okay. And for it to go back and forth once, swing, swing, that's one full cycle, right? That t time period is equal to, and this is on your AP equation, right? 2 pi times the square root of L over G. Okay. You guys remember this? Okay. Did a whole lab to figure this out. Okay. So capital T refers to time period. Okay. L is the length of the string, G is the gravity field. Notice what's not in this though. And of course, you guys remember this from your lab because you figured this out experimentally. So that the mass of the bob doesn't matter. So as long as the mass is located in the bob, but then, yeah, so that's consistent with the Galileo experiment, right? So more inertia, more force, gravity force, two effects cancel out, right? Same acceleration, right? And also the starting angle also doesn't matter, right? As long as it's, AP might want you to specify a small angle, but it says that, right? Right. And then remember, AP likes to ask questions around either something to do with graphs. You see a lot of graphs, like you guys see proportional questions. Like if you make the length 4 times as long, wouldn't that double the time period, right? Or what if you had 4 times the gravity field? Wouldn't that be like half the time period, right? So be able to do that. The other oscillating type motion you see quite a bit, and this could be for either a vertical spring system or a horizontal spring system with no friction, although they could add friction, just make it a little bit more complicated, is a mass on a spring, where the mass and the spring constant. And so a very similar looking formula. Just remember, time period equals 2 pi times the square root of m on k. Is that so? Okay, where m is the mass of the block and k is the spring constant. Okay. How about this? What if you were asked to make a graph based on experimental data? So you can switch out this M, you can put different masses here. And again, this might be a vertical spring. That might be a little bit simpler setup, right? Or a frictionless surface horizontal, right? So you can switch out the M. You can calculate you can measure the time period with the stopwatch, okay? And you have to make a graph so that the slope of the graph represents this k. Okay. Can you guys see that? Right? So I want to see if you guys can stay a step ahead of me. Like if you're taking notes, see if you guys can beat me to the answer. Okay. How can you rearrange this equation so that you could make a graph where the slope of that graph represents a spring constant? Can you guys do that? Right. That would be a really classic AP question, wouldn't it? Okay. Can I rearrange this formula to get into the form like y equals kx, y equals kx? Can you do that? Okay. Well, let's try it out. What I'm solving for, let's see, it's not only is it in the denominator, it's also buried inside a square root. So I need to handle both those things, right? Maybe I'll start by squaring everything. That would get rid of the square root, right? Can I do that? Can I do the time period squared is equal to 2 pi quantity squared times m over k? Okay. Now, that's not exactly what I'm looking for, but it is a step closer because the square root's on. Okay. Oh, hey, how about this? What if I cross multiply with the k? Right? Would that look like this? Maybe 2 pi quantity squared m is equal to k t squared. Would that be true? Now, this isn't the only way you could do it, but this could be one of the solutions, because look at this. Isn't this like y equals k x, right? So, I see what you could do with this. You could totally have a graph where you put 2 pi quantity squared mass up here. You could put the square of the time period here. And if you got a bunch of experimental data, I can tell you what this would look like. It would, all the points would line up in a straight line. Of course, you want to scale your axes and right the whole bit, right? But the slope of this line would be exactly the spring constant. Okay, you guys see that? Right. Now you have to manipulate the heck out of those axes, but we've done that a bunch of times in this class, including a bunch of labs. Right? You guys remember that? Right. And another thing that tell you guys about oscillating motion, right, is let's look at a set of graphs: x versus t, v versus t, a versus t. Okay. No, this is a set of graphs that you guys have seen over and over, even since like unit 1, kinematic motion. So x versus t, v versus t, a versus t. Okay. So of course, all the times are in seconds, seconds, seconds. X could be in meters, centimeters, some version of that. V might be in meters per second. A is meters per second squared. Right, some version of that, right? Right. And then now this set of graphs, what story is it referring to? Well, I just gave you 2 stories that it could refer to. Okay? It could refer to some of the position, velocity, and acceleration of this bob on the pendulum. It could refer to the position, velocity, and acceleration of this mass on a spring. It could be horizontal, exactly like I did here, maybe horizontal frictionless, right? Or you could just hang it from a ceiling, pull it down with boing. It'd be like the same story vertically, wouldn't it? Okay. And what would these graphs look like? What shape would they take? Do you guys remember sinusoidal? Okay. So say you could start with either a sine or a cosine graph, depending on like where you started. Maybe I'll just start with the sine graph, right? Just for example, right? You guys remember what a sine curve looks like? Looks like this, and it just oscillates. Like you just like going forever like that. Okay. Where there's a time period associated with this. Here's that capital T time period on those from that equation. Right, you guys remember that? Right. Ops for one full cycle. Okay. In fact, if you make a circle like a unit circle, right, and you watch a dot going around at constant speed, kind of like a race car going constant speed around a track, right? Then the vertical position of that dot relative to the center of the circle, right? So sometimes it's 1 unit up, sometimes it's 1 unit down, sometimes it's like at the same level as the origin. Right? That is exactly a sine curve, right? That's what that looks like. All right, and then how about the rate change of this? Well, if it's at 0 position, then it's actually moving. Wouldn't it be true? Here, how about this? If this bob is going through the center position, that it might have 0 position relative to this center dash line, but it's also moving as fast as it's ever going to move. Same thing with the block on a spring, right? If it's going through the equilibrium point where the spring is either stretched or compressed, right? Then wouldn't it be going the fastest it'll ever go? What I'm trying to get at is this: these nodes of the x versus t exactly align with the maximum speed of v versus t. Okay, so here, actually, maybe I should kind of line this up with dash lines. Now, these are not for vertical asymptotes. It's just I'm trying to line up these graphs. Okay. Okay. And this would go like, whoops, messed up already. This goes like this. Okay. Where where x is turning around, that would correspond to 0 velocity. Okay. Okay. And if this top one is like a sine curve, for example, this is some version of x equals maybe amplitude times sine of omega t, something like that. Wouldn't this be the cosine of that? V equals cosine. Right. Got a little chain rule in there, getting a little bit more in depth than if you need to, but right. And then how about a versus t? Right? If it goes sine and cosine, do you flip back to sine except negative? Right? But you definitely knew that if you're taking a calculus class, right? Rate change of sine is cosine, rate change of cosine flips back to negative sine. Right? So it looks like the first graph upside down. And then if you wanted to take the rate change of acceleration, that's called jerk. Right? And then that would go to negative cosine, and then there's be like 4-part cycles over. Right? Okay. You guys remember this? Okay. All right. So that is in broad strokes a recap of Unit 6. Right. So I'm going to throw you guys an FRQ and next part of the class.